So there's a Peanuts comic strip in which Charlie Brown and Linus are looking up at the sky, and Charlie Brown is seeing barnyard animals, and Linus is envisioning this incredibly complicated display from the Bible. Meteorologists do not look at the sky like that. Now, there are other kinds of meteorologists, and they look at the sky in a different way. For example, our friend in Philadelphia, Puxatawny Phil, does weather forecasts. Now, a meteorologist doesn't do it that way. We are physical scientists, and because of that, we translate that science into the language of the discipline, which is math. And math is, in this situation, is math in action. It's applied math. And so it means that we're translating things that we can then do action upon as, for example, forecasting. So that's a projection into the future. And so when an atmospheric scientist looks at the world, this is what we see. We see these equations. It's a solar-powered system, and so it drives the atmosphere like a fluid, and so you can write down the fluid dynamical equations, and then you can project how that will change in the future simply by writing the math down and solving it. So how do you do that? Well, it's a lot of calculation, and so you need massive computers to actually solve those equations. That produces tons and tons of data, a sea of data, if you will, which we then visualize and understand how that leads to changes in the weather or to the climate. So how do you get started in this? So for me, I grew up in the Boston area, Boston Red Sox fan, so I was interested in statistics. So that's actually how I got interested in math. Then I went to McGill, and then MIT, and then I began wearing this strange raincoat with mathematical symbols on it. And so this led me down to a path of using math to look at storm systems like this. This is what's known as an explosive cyclone. It's a bomb cyclone off the east coast of the United States. And if you look at that satellite image, you can see a lot of different cloud structures there. And each one of those is saying something different about the meteorology in that area. To understand that, you have to translate that into math. And that translation has led to tripling of lead time for storms like tornadoes. And so that extra 10 minutes can mean life and death, literally, for people. And it's the translation of that into these computer models that allows us to do that. And underlying that is the mathematics. We also verify what we're doing. And so we can look at probability of detection, our hit rate on our forecasts. We can look at the success, which is 1 minus the false alarms. So how many false alarms are we getting? That provides us with a measure of our skill and also the bias in the forecast. And so that's a way of calibrating the math that we're using. This all goes back into chaotic dynamics that Ed Lorenz, one of my mentors at MIT, talked about, which is sensitivity to initial conditions. It also ties to the fractal geometry of cloud structures. And all of that is an important part of mathematics. Also, data science is a term you hear a lot about. Deep Blue, about 20 years ago, beat the world champion in chess. Recently, IBM Watson beat the Jeopardy champions. And more recently, AlphaGo, a computer program, beat the world champion in Go. And they didn't stop there. They went further and actually built another computer program to beat them. You can also look at math in the terms of individual particles or agents rather than continuous equations, and understand how individual agents such as professors in a university or faculty and students across a UW system like I'm showing here actually evolve. You can do this for the complex ecosystem dynamics between predator and prey, and you can actually use that concept, as I'm doing now, to actually drive computer programs to write other computer programs that do weather forecasts, and use the coevolution to actually drive better and better predictions. Of course, that kind of system, because it's evolutionary, is adaptive. And so it can change as the inputs change, either because the seasons are changing or because the information that you're feeding into it is becoming better. It will adapt to that information and become a better forecast. So that's a way of actually using the mathematics that underlies that. So what does that mean to people who are actually using this information? That's this complex decision web. So you might think that the algorithms take over everything, but in fact, that's not the case. The context is critically important. And so that's providing us the tools to understand the situation, and that's where the human comes in, making those decisions based on that. So what about climate change? If we think about the Great Lakes water levels, or Lake Michigan, for example, it's about 3 billion bathtubs full of water, which seems like a lot of water, but it goes up and it goes down at some pretty significant intervals. Over the last 30 years, we went from a record high in 1980s to a record low in 2013. And the way to understand that is to talk about a budget, just like your bank account. So there's input into it, precipitation and runoff into the lake, and evaporation out of the lake drives those fluctuations in the lake level. And we know from climate change, and this is showing about a 20-year period from 1992 to 2010, we saw increases in the lake water temperature of about 10 degrees Fahrenheit. And that leads to significant evaporative increases, which is water loss. And so what you're seeing there is the impact of that water loss in places up in near Green Bay. So we can make a model of that. We can use some other mathematics to actually structure the basin correlations, the connection between the meteorology in all of the individual basins, like Lake Superior or Lake Michigan or Lake Ontario, and actually use that to understand what the fluctuations will look like in future climate. All of that is driven by mathematics. So understanding the mathematics, connecting that to the physics, using that information to make predictions and understand the future. It's all based on math. And that's my story. So thank you for your attention.